Okay, screens readjust. There we go. All right, yeah, so dynamic linking. What is it? So dynamic linking is basically the idea of taking different programs, not really programs, we'll just refer to them as just like executables really, and taking functions that one exports and linking them into another one. So, for example, you've probably heard of libc before, or almost certainly of OpenSSL if you haven't. And each of these are shared libraries which export certain functions that you can use. So libc, provides basically all of the standard library functions. So fopen gets, prints, printf puts, like more or less anything that you've used in like common C. Again, OpenSSL provides a lot of common encryption routines. And this is in contrast to what's called static linking, where basically instead of just pointing this program to this other executable, we put everything that the program will ever need into its own binary. So, why do we do this? Basically, just like imagine how big things could get if every Hello World program also had to include all of libc that's needed. Yeah, so I have literally Hello World in C, right? And if we look at the output binary, it's 12K roughly, right? However, if we compile this statically, including all of libc that's needed just to print Hello World, it's now almost a meg. Right? So this is not good. This is literally just using printf, and in this case, this isn't even printf. This is actually dissolving into a puts call. So this doesn't include any like parsing stuff. This does not include network operations. So even I would say relatively simple programs could turn into like 10, 20 megs each, which is just not a good thing, right? Especially when you have all these common functions, why are you duplicating them everywhere? The argument can be made that, we want a specific version of something so that, it can't break us if you have like an old version of libc or something. However, it's like these functions have a defined API, right? If libc ships with a bad function, that's a really big deal. That's not just going to go and why you would statically link, or if you want to just like, if you have, it's also simpler because you don't have to have a linker. You don't have to have the thing that actually points all of these binaries to each other. But besides that, in very, very few cases now will you actually see statically linked binaries. Yeah, so how does this actually work internally? So libraries, all of the programs that you run, or all the programs that you build by default have symbols in them, which say this function is at this address and is this long. This other function is at this other address and is some other length. And then if I want to export those, you can build the program as what's called a shared library, like I said earlier, and in GCC you just do -shared. And that will change up slightly the file format to say, this is not just a standalone executable, but I'm going to take all these functions, I'm going to keep all their symbols in, and I'm going to just say this is a shared library that other things can link against. And then the programs that want to link have a number of things. They have a relocation table, which basically says, I need this function. They have a global offset table, which basically says, once I have this function, where, like, I need a place to store where this function points, or where this function actually lives in memory, right? If my Hello World program requires libc, libc is going to be loaded into virtual memory somewhere. And I need to know where that somewhere is so that I can efficiently jump to printf or whatever, and I don't have to do a resolution for every single function call. And then lastly, they also have these function stubs, which are what's used before it's resolved to actually invoke the linker to resolve the function. When, like it says, as soon as the function is called for the first time, the linker will, the stub basically what's at the address where, let's say, printf is expected to be local in the binary, there's a little stub that basically says, okay, let's actually invoke the linker and pass it an argument that says, give me the address for printf. The linker goes and does its magic. We'll basically skip over that entire part because that's like lower level than we really care about. And then once that's done, it actually replaces in the program's virtual memory the address where printf is. So no longer is it pointing to the stub, it's actually pointing into libc, where printf can actually be found. And then after that's done, the address is considered resolved, and you'll never have to go through this like stub lookup again. So this probably is confusing because it's kind of, whoa, okay. So let's actually go through in Binja and in GDB and just kind of look at this as it goes along. So again, we'll use this very simple Hello World program. Don't care about the static one. And let's open it up in Binja. So we go on to main, and you can see this is all the program. Again, this is the same thing that if you compile it statically becomes almost a meg of code. So how does it work right now, though? So this call to puts, this is not calling libc's puts, right? The program has no way of knowing where libc is when it starts off. It's somewhere in virtual memory, and we need to find it. So puts right now, actually, like Josh showed, this is actually a little stub in the program which jumps to a dereferenced offset. This is a good thing to note, right? This is dereferencing other stuff in our code. And we're dereferencing that and then jumping to it, which means there is an address at this puts it got, which we're jumping to. So keep this in mind in just a little bit, actually. And you can see, so right now, by default, puts says, okay, the puts function is at hex 400-406. This is, again, not where libc lives. This Binja has no way of knowing where libc is going to be loaded at runtime. So what does this do? Well, Binja doesn't actually identify this as a function. We need to tell it, and what this is doing is we go through another jump loop. It's pushing 0, which basically says to the linker, this is the 0 indexed item in the relocation table. So it's basically just telling this next jump what to grab, like what to ask for. This jump then ends up going here, pushing another constant, and then jumping to another dereferenced address. This dereferenced address is automatically filled in at load time with basically where the linker lives in memory. Again, if we look at this right now, this is all zeros. That's obviously not going to be valid. But if we run this under GDB and look at this, you'll see this magically gets filled in when we go to main. So let's do that, actually. Let me bring up GDB. Yeah, so again, running hello world. Let's break into main. So this is going to be after everything has been loaded, but before puts has actually been called. So we'll run. We hit our breakpoint, as we expect. And now if we go back and we start to look at some of these addresses, let's just take a look at 6010. All right, so you'll notice a couple things here. So this constant, 600E28, this is just in the binary, right? However, we now have some of these zeros that got magically filled in, right? Everything from this 0, yeah, let me make this a little bit larger. Let's do 30. All right, yeah, so everything from this 0 through here has now actually been filled in with some pointers. And you can see GDB is even telling us this is the dynamic linking runtime resolver. Ignore the last little bit. But, if we go back to where printf or where puts is supposed to be, should be somewhere in here. Where is it? Ah, here it is. So it's 601.018. You can see this is still pointing to our local thing. So if we're going to step through this. So you can see we hit this call, which then, this is, GDB is automatically skipping over the resolution part. That's not helpful, actually. Regardless, so let's go through what's actually happening. So we call this puts at PLT. We're going to set a breakpoint with that PLT address. And now you can see we've got that push 0 and then a jump. And then again here you can see there's this, the resolver has been magically filled in for us. And if we just step through this. Well, okay, now we're in runtime resolve. We don't care about that. We'll run this one more time. And now, oh, I forgot to delete the breakpoint. That's not what I wanted. Run ni. There we go. Okay, so puts has been called, but now if we look at this exact same address that we had before, not that actually. Let me go back up here and find it. Or we can just look over here. 601.018. This has now magically been resolved into a libc function, ioputs. And so this has basically gone through the resolution chain, and any subsequent calls to puts will still go through this first dereference, if I can find it. So they'll still go through this dereference, however this puts at got address is now directly into libc. So instead of bouncing around like 5 times like we did before, it's just a single call into this function, which then dereferences something and jumps there. So it's a lot quicker, right? We can all see that. We aren't jumping around the program a lot anymore. We're just jump, and we're in libc. This is obviously still not completely optimal, but it's much better than having to resolve this every single time that we wanted to call any libc function. I think we can all agree on that. So this is at a very high level, how the linker works. And if we go back in to the slides, we care about this now. So all of those function at got addresses, those are essentially function pointers, right? They're essentially an array, because they all happen to be in sequence, of addresses in libc where specific functions can be found. And we know when one of those is called that we'll go through that, dereference that address, or dereference the local process's address, and to get the actual libc address, and then jump there. So what's nice about this, though, is that the addresses where the libc addresses are, if we go back, getting everybody confused, these addresses, again, where this is resolved after puts is called, but these are constant, right? This is always the address where libc is located, where the libc address is located, is always going to be this 0x601.018. And what's nice about that is if we get any type of like write what where primitive, which is a very common thing to end up getting, we can now reliably, first of all, read where libc is, which is useful, and we'll see why that's useful later on. But more importantly, we now have a known place where if any libc function is called, we can kind of, if we put our own function that we want to go to here, as soon as that libc function is called, our function gets called, right? We have this specific place in the program where these are all function pointers and they're used all the time. And if we can overwrite any of these and then get that function called, we can get IP control, right? We can determine where the program goes from there. So this is basically just, this is what's called a got override. This is particularly useful if you have basically a one-shot shell function, which basically just means I can just jump to an address and then get a shell. This actually happens more frequently than you would think. There's some fun magic addresses inside of libc itself, actually, that you can just jump to get a shell. They're in basically every version of 64-bit libc. You have to find them, but they're like finders online that will give them to you. But again, that requires knowing where libc is, and we'll get to all of that next week. But we have, again, this place where if we can just put data, we can get control. We don't need to have a stack overwrite. We don't even need to know where the stack is. We can just write to a constant address, and then, in theory, pretty easily get some control flow. So, this is obviously kind of a big deal. So what have people done to mitigate this? So there's this thing called RELRO, which is relocation read-only. It basically does as advertised. It sets the actual pages where the relocations live to be read-only, so that you can't write to them. This has 2 variants, though. There's partial and then there's full. Partial rel-row, in our case, doesn't actually do anything against the exploit, and partial rel-row is what's enabled by default for compilers. So by default, if you can get a right one where you've got code execution, more or less. Full rel-row, on the other hand, actually essentially forces the pre-resolution of all of the symbols that you ask for, dumps those into the GOT, and then marks it read-only. So in theory, you could still get around this, but that would require you to mprotect the page back to be read-write. But at that point, you've already got IP control. So why are you doing this? You might as well just jump to a magic address or jump to a GIF shell function or something like that. Yeah.
Why is partial rel the default?
So partial is the default because what happens with full is you require all this pre-resolution, which can hurt loading times if you have thousands of imported functions. Because say let's take like Chromium or something. So if there's a useful utility called LDD, which will show you all of the. Oh yeah, that's a good point. Oh boy. What is this actually going to be executing? Let's see. Let's open up Chromium and PS on it. And stop nagging me. Oh boy. So somewhere in here, there it is. This is our actual executable. So if we LDD on this, you can see this is a lot of shared objects that it's requiring. All of these. And so if you want to preload all these symbols, you have to find every symbol that you want imported. It doesn't actually say from which library it wants imported. So every single function that it wants, you have to walk through all of these shared objects to find. And then you have to do that again for the next one, and for the next one, and for the next one. And this is tedious, as you can see. Chrome is, again, a very big application, but it gets, it gets the idea across. This could easily bump your startup time by multiple seconds, even on an SSD with plenty of RAM to cache all these. You're still looking at quite a bit of parsing. So yeah, that's why it's not the default, basically. But yeah, so a very good question though. So let's kind of go through this a little bit, just to because there's a lot of layers to this, right? You've got potentially upwards of 3 jumps when you're doing the initial linking, and then there's just this magic new section that happens to have function pointers and all this kind of stuff. So let's go through a concrete example of this. I don't care about that. So I put together a very tiny function that or a very tiny program where essentially it wants an address from you and it wants a value, and then it's just going to write that single value to that one address. That's it. That's all the control that you have over the program. If we open this up in Binja, go back into GraphView. Come on. Yeah, so you can see we get an address. And then we get a value. Here's where we actually do the assignment, and then we call exit. There is something to actually note here. We don't return, we explicitly call exit. Exit is probably one of the most commonly used functions that you'll be able to use this technique with. Because one thing that you have to be careful with when you're doing GOT overwrites is if you need multiple stages to set up the overwrite, say you can only write 1 byte somewhere, if you corrupt a function pointer that's used in that chain to write, well, you can't do that, right? So exit's very common for this because it's usually only, it can only really be called once, and usually it's very controllable when it's called. In a lot of CTF challenges, you'll be able to exit the menu and they'll explicitly call exit, or if you take, if you enter an invalid number, it might explicitly call exit on you so that, presumably the number parsing is potentially down 4 or 5 function layers. So instead of having pass an error code all the way back up from that, they just exit directly. And so you get a really easy way to reliably call exit. So it's a very common thing that you'll want to overwrite. And you can see we also do have a GIF shell function. Again, libc can do magic with libc, but this requires leaking a libc address, and we'll talk about all this more next week. But yeah, so let's kind of just go through this as a collective. We have exit, right? We have this exit at got pointer. This is unresolved, points to the stub. However, can somebody tell me what address we will need to overwrite if we want to jump to our give shell function by overwriting exit's got address? It's up there on the screen right now. Just what address will we need to tell this to overwrite? Yeah.
601.038.
Yes. Good. All right. And then the address of give shell is right, because all we're doing is effectively calling this address. So 0x400.626. So, and I've already forgotten, was it 0x601.038? Does that sound right? Let's try it. 601.038. Yep. Okay. And the address of give shell 400.626. So there are the constants that we need. I was very lazy and did not make this accept hex numbers, so we do need to do the conversion. And let's walk through this. So we go to main, start it up, and actually let's just break right in here. Alright, so this is the address that we want to write to, and this is the thing that we want to write. So at this point, it's good. We're going to just we're going to load our variables off the stack, and then here's where we actually do our assignment. So you can see we're throwing RAX into the thing at RDX. So you can see indeed RAX is our give shell function, and RDX is this got pointer. So if we now step again, this call to exit is now actually jumping to our overridden address, and you can see now we're in give shell. We've now magically made our instruction pointer give shell. And if we continue, well, outside of GDB, find the numbers again. A shell has appeared. Amazing. So, this is the basic idea with got overriding. Again, you have this constant area in memory that has function pointers that are used all over the place, so let's override them. Why not? This ends up being the end goal of a lot of exploits, because, again, full railroads, I wouldn't say never enabled, but it's certainly pretty rare. And even once you have, it ends up being incredibly useful to turn a write primitive into, a code execution primitive, as you can imagine. So this ends up, like I said, it dissolves down into a got override a lot of the time. Though, again, you do have to be very careful because you can't use any functions that you use in the process of actually creating or of actually overwriting the data, which in a lot of cases, it's not as simple as write what where. They don't give that to you, but it ends up coming through multiple stages where you're definitely going to be going through some reads and some writes. Sometimes you can chain this together with a lot of other things. So say you have an address on the stack, you can overwrite and that you read into that. If you can overwrite that address, you can point that address to a got entry and then read over the got entry and then call it. It manifests itself in a lot of different ways, right? But it ends up being a very, very common exploitation technique, especially when combined with like libc magic addresses. Yeah, you can do all kinds of crazy stuff with that. Let's see. So that's that. Let's see. Actually, this was one other thing I wanted to just show off really quickly. Did I already? I did. Let me just create the hello world again. I wanted to just open up the statically linked one in libc really quickly so you guys could see what it looks like. It's pretty messy, but it is useful to know because, well, so if you ever get a binary like that, you'll probably be able to pretty quickly tell because it's very large, right? If you ever get a binary for a CTF challenge that's like over a couple hundred K, it's probably statically linked, and you're going to have a really bad time. Let's see. What was... There we go. Okay, yeah. So again, you can see when we build statically, it all still works. The binary is incredibly large, though. And if I bring it into Binja, not PowerPoint. Yes, I don't care. So, yeah. In this case, we also got lucky because a lot of times CTFs will be very cruel and they'll also strip all symbols out of the binary, especially with static libc stuff. Because if the binary is completely self-contained, you don't have any resolutions to go through, so all of the functions can be whatever, like, can be named whatever. The only reason that we see call printf in normal binaries, even when they're dynamically linked, is because the linker has to know that it wants printf, right? And all of these functions are actually keyed off of name. This is why there's some nasty tricks that you can do also that have to do with dynamic linking that I'll talk about in just a second, actually. But this is why even if you have a completely stripped binary that's dynamically linked, you can still figure out what's puts, what's print, all of the libc functions. However, when it's statically compiled, you can remove all of this information and everything is now just like one of these sub underscore functions, and it becomes like impossible to read. But yeah, so you can see in this case, there's our main. However, now we have to like go through printf, and then you go through vf printf, and then you just walk down this massive chain to actually get to the system calls. You really should never have to do this, but it is always fun to just see, this is what printf requires. All of this. Anyways, yeah, so one other thing that I did want to mention briefly, this is not really useful for CTFs. What? Yes, good point. So even if all of these are stripped, you can still sort of, most of the time, recover the functions, sort of. Because, printf is very well studied, basically. So it has a very well-known signature. And that signature basically means its control flow graph looks like this, and there is a call here, and this is stood out, and this is VF printf. The thing that printf calls looks like this, and you can use these, and IDA has this built in, to basically reconstruct function names based off of how the functions look. So it combines that with a few other things, but I believe it's basically just control flow and where the calls are. But yeah, IDA can sort of do this. It works pretty well, but it's not guaranteed because again, it's an imperfect science, right? If you create a function that happens to look the exact same as printf that calls the same things, it's not going to know that, or if it's actually like libc's printf. But yeah, that's a good point. You can sort of do that. So yeah. Anyways, so what I was going to talk about, this is not really relevant for libc's, but for CTFs, but does have to do with what I was saying with dynamic linking and how everything's keyed off of the name. If you want to, you can actually do some, well, let me restart. The linker and the loader actually have some magic environment variables that they read off of, and what you can do with those is you can basically say, in addition to looking for all of the shared objects in libc, let's say, also look here, and it will find, for instance, any of the shared objects in the directory that you specify, and look for symbols in those. So if you want to change what puts does, you can actually create a small program with a function called puts that does what you want it to, put it in the directory, and then I always forget, it's ld preload.
You can do ld preload
LD library path, that's the one. You can do LD library path equals like dot, for instance, and then that will also cause it to look in the current directory for shared objects to load. So we could define a function called puts, just have it like return 1, and then if we ran a dynamically compiled binary with this LD library path equals dot, puts will just do what we want. This is useful sometimes if you've got really weird debugging things, or if you need to do really weird things against like precompiled code bases. Because you can, for instance, let's just like log all of the calls to puts, or let's log all the calls to, maybe some network operations might be a little bit more useful. So yeah, this is just like a useful thing to know. Again, has basically nothing to do with CTFs, but is still sort of fun. Let's see, yeah, so...
Preload is actually sometimes very useful in CTFs.
Do you have an example?
I solved the problem with it last week, so...
Which one?
There was a function in HackLU last week, or there was a reversing challenge in HackLU last week. It was like super Maya end of the world themed, like the Mayan, like on December 12th, on December 21st, 2012, or whatever, the world's gonna end. And they called a function time and checked if it was equal to if the day was December 21st, 2012. And if it was, they like did some crazy math and gave me the flag. And so I solved it by just overwriting the time function with the thing that always returns that time, or some time on that day, and just spat the flag with an LD preload.
Yeah. So this is a good point. If you, I was saying more in the context of like pwning, but yes, if you have reversing challenges where like there's constraints around some like what should be a constant, from system, well, you can make it do whatever you want. So maybe it's not. But yeah, so a useful thing to know, nevertheless. It is just about 7. Does anybody have any questions about linking or relocations or things like that? Yeah. In what context exactly? Like. So generally, let's see. So this is going. So there are 2 different like stages here, right? Because when you're running the program, like if you're building a standalone executable where you have the same function defined twice, GCC I don't think will even let you do that because it's ambiguous which one you're calling. In theory, you could actually modify a shared object to export the same symbol twice, and I believe in that case it would pick whichever one was defined later.
I think what you could have been asking was with the dynamic resolver.
Yeah, so that's what I'm saying. So yeah, like if you have basically, or I think it's probably actually, it's whichever one would come first. Actually, yeah.
Well, you can like call the dynamic resolver. It's a function in your binary.
Yeah.
Which I think is what he was getting at.
Okay. Yeah. So this is also. This brings up a good point with not only is there like the DL runtime resolve AVX or whatever that we saw earlier, there are actually, you won't see that itself used a lot in like normal code. However, there are these functions called DLSym, DLOpen, DLSym, and those are the main 2 that you need. And those can actually open, like you specify what shared object you want in C, and it will open that and can actually hand you back function pointers. So I actually had to do this for some research that I was working on where we needed to hook send, I believe. So we have a network socket open and we're trying to send data through that, so we needed to hook that function. So what I did was I said, we're going to use LD preload, and we're going to write a quick send that also just like logs out what it's doing. But in addition to that, I need to actually get a handle to the original libc send. So what I could do is I could actually just DL open libc, and then just ask the resolver to give me the symbol for send, and then that hands you back a void pointer. Well, yeah, it's a void pointer. That is just the address of send and when it's loaded at runtime. You will see that used sometimes in actual code. It's usually not, if you see it, it's usually kind of weird, but it does exist and you will see it sometimes, especially if you need to do like weird hacks like that, like hooking send, for instance. But yeah, no, there's lots of weird and wonderful things that you can do with like confusing the linker. But yeah, if you could, like I said, you could in theory export the same symbol twice from the same program. For all I care, that might actually throw off disassemblers. I've honestly never tried that. So
Yes.
yeah. So yeah, there's lots of fun things you can do because
Actually, most of them don't. Well, they don't get a name for the second one. I'd actually give them both names.
just like _1 or something.
When I checked like a year ago, Binary Ninja just doesn't name the second one.
Okay.
I don't know what Renori does. It probably messes up.
Probably. Probably.
I mean, Object Note probably doesn't mind.
Or it crashes.
Hopper probably doesn't do it, right?
No.
Uh,
But yeah, so
yes,
the
there are lots of very good anti-disassembly tricks you can do with just the symbol table.
oh yeah, this is also completely unrelated, and I don't think we've seen a CTF challenge around this yet. But the actual relocation table that I was saying, which describes like just this is the symbol I need and put it here. It's not only good for that, you can also do arithmetic and some conditions in it, and it turns out the relocation table is actually Turing complete. So you can actually implement an entire program inside of the linker.
Some people from Dartmouth implemented a breakup interpreter that makes it use at load time.
At load time. So yeah, again, this is a very weird field or very weird thing that all operating systems have, right? Everything uses dynamic linking because why repeat libc functions or equivalent if you can just dynamically link them in, and there are lots of weird things that you can do because of how they're implemented. But yeah, so I believe let's go and take a break since it's just about 7. We'll come back and we'll talk about something. We'll probably go over homework or the midterm stuff. That's also a good point. Yeah.
So if you have specific problems you want, that's what we're going to be talking about.
Yeah.
Because it seems like a lot of people had trouble on the previous two homeworks, and we want to fix that.
Yeah. We want to make sure that everybody's really comfortable.
It's only going to get harder.
Yeah.
So.
So yeah. Anyways, we'll reconvene around 7:15, let's say. So, cool. Light's coming on. There they are.